experiment in general chemistry, okay? And there's a lot of moving steps, and we want to go through those steps as concisely and quickly as we can today, but I want to start with the overall reaction. Okay, am I on the screen? All right, which is blue dye plus bleach yields colorless dye plus salt. Okay, and all of these things have a state of matter of aqueous. So this is essentially what we're trying to accomplish today. So whenever you guys use bleach at home, which I'm going to go ahead and assume everyone's used bleach before, it removes stains from clothing. What people commonly think is it actually removes the thing making the stain. That is not true. What actually happens when you add bleach is it makes the thing making the stain invisible or colorless, so that you no longer see the stain. The molecule is still there, but you can't see it, so everybody's good to go. So what we're going to do today is we're going to take this blue dye, literally just blue food coloring, the same you'd find in a drink of blue Gatorade, okay? And we're going to add to it a milliliter of bleach. And what do you think is going to happen to this blue food coloring? It's going to disappear. And when we take this out of our device, it's no longer going to be blue food coloring. It's going to be a completely clear solution. So this is something you've all done before, but you probably haven't studied the reaction. And what we're going to do is we're going to study the kinetics of this reaction. Or said another way, how fast the reaction occurs, or what are the reaction order with respect to each of the reactants. So what we want to have is the rate of the reaction, and we know the equation. It equals K times the concentration of dye to some power that we're going to determine experimentally, times the concentration of bleach to some power that we're going to determine experimentally. Note that even though this is a one-to-one reaction, we cannot assume that M and N are 1. We actually need to do the experiment and figure out what they are. However, in order to do this experiment, we need some stuff. Okay? We can't just go into the lab and have all the stuff we need. Namely, the two things that we need is we need 100 milliliters of 8 times 10 to the minus 5 molar blue dye. And what we have on hand is 2 times 10 to the minus 3 molar solution. So if we need 100 milliliters of 8 times 10 to the minus 5 molar, and we have 2 times 10 to the minus 3 molar, we all know that we use what equation to solve this? C1V1 equals C2V2. So all of you have used this equation before, and you're going to use it again here, and you can just write down the answer when we get done with this here. So our initial concentration is 2 millimolar, or 2 times 10 to the minus 3 molar. We want to figure out how much of that we need. We need to make 8 times 10 to the minus 5 molar, and we want to, I'm just going to move this over a little bit, we want to make 100 milliliters because that's what the lab manual says. All right? When we do the math, multiply the two numbers together, divide by the number next to the variable, we find that V1 is 4 milliliters. So we're going to take 4 milliliters of our 2 millimolar solution. We're going to essentially add 96 milliliters of water, and we're going to end up with a 8 times 10 to the minus 5 molar solution. All right? The other thing we need to make is sodium hydroxide. In order to get this reaction to occur so we can study it kinetically, we need to have this in basic solution. So we're going to need some sodium hydroxide to do that. To do that, we need 150 milliliters of 0.1 molar NaOH. And on hand, we have 5 molar. Now, 5 molar NaOH is dangerous. It's caustic. If it gets in your eyes, that eye's not going to work anymore. So please make sure you're wearing your goggles when you're handling the 5 molar NaOH. It is nasty stuff. Mathematically, however, we do the exact same thing that we did before. C1V1 equals C2V2. In this case, our initial concentration is 5 molar. Our initial volume is what we're trying to figure out. Our final concentration is 0.1 molar, and we want to make 150 milliliters so that we have enough to do the whole experiment. V1, in this case, is 3 milliliters. So in this case, we're going to add 3 milliliters of the 5 molar sodium hydroxide solution, and then we're going to add 147 milliliters of water to that to make a total of 150 milliliters. So just to recap very quickly, our goal is to figure out basically M, N, and K, okay? But in order to do that, we need a couple of solutions. So these are the solutions we need and how you're going to actually make the solutions in the lab. You can't use the solutions directly from the lab. So now what we want to look at is how are we going to actually determine this rate law. All right, let me see if I can put that there. All right, how are we actually going to determine the things in this rate law? Well, what we're going to use is a spectrophotometer. And instead of concentrations, we're just going to use absorbance. And as you guys know from the past 2 experiments, absorbances and concentrations are related to each other. Said another way, if something has a higher concentration, it absorbs more photons. For the very simple reasons, there's more molecules between the source and the detector, so more of the photons cause electrons to move to higher energy levels. So we don't actually need to find the concentration. We can use the absorbance directly. So that's basically what we're going to do. And we're going to make this new assumption. All right? We're going to design this experiment. And this is a little bit complex and a little bit beyond the scope of this course. You just have to take my word for it that this works. We're going to design this experiment so that the concentration of bleach is constant. Okay? We want the concentration of bleach to be constant so that we can evaluate the concentration of dye. In a kinetics reaction, if you want to make something constant, you make it really high. Because if it's really high and some of it gets used up during the reaction, it still doesn't really change that much. Said another way, we're going to make it at 0.7 molar for the bleach. So this is a huge concentration relative to the 8 times 10 to the minus 5 molar for the blue dye. It's a huge concentration. Said another way, its concentration is within reason constant. Then this allows us to do something mathematically that's important. It allows us to define what's called the pseudo rate constant, K prime. And we set that equal to K times the concentration of bleach to the N. Because now we can assume that the concentration of bleach is constant. If we combine these 2 equations, and again, this is a little complex and not super important, okay? If we combine these 2 equations, we get the overall equation, which is rate equals K prime, the pseudo rate constant, times the concentration of dye to the N. So now we have one equation that we can evaluate. If we use this, there's too many variables. We can't evaluate it. So we have to do something, a trick, if you will, to make the math easier so that we can actually evaluate the expression or minimize the variables. So now, using the pseudo rate constant, we have an expression we can validate. And what we're going to do is we're going to determine whether M is 0, 1, or 2, right? 0 order, first order, or second order. In order to do that, we're going to use what's called the integrated rate constant. And for a 0 order reaction, the integrated rate constant, 0 order, is concentration dye at some time equals, am I not on? Good. Negative K prime T plus concentration dye 0. And you don't need to know calculus for this course. This is given to you in the textbook, okay? They do the calculus for you. And we end up with this integrated rate law. The integrated rate laws are extremely useful because they allow us to investigate the concentration of dye at some specific time. You can't do that from the rate law. You can do that from the integrated rate law. You'll also notice that this is y equals mx plus b. So if we put on our y-axis the concentration of dye, or the absorbance of the dye, and on the x-axis time, if we get a straight line where the r squared is close to 1 when we do a linear regression, then we know that it's 0 order. It could also be first order. And for the integrated rate constant of a first order reaction, it's ln of the concentration of dye at some time equals negative kT, am I still on the screen? Plus ln of concentration of dye at time 0. Again, we have y equals mx plus b. If we graph this, where the ln of the concentration of the dye, or the ln of the absorbance, is graphed versus time, and we get an r squared with a linear regression of close to 1, we know that it's first order with respect to dye. And then finally, we could possibly have a second order reaction. And that is 1 over the concentration of the dye at some time equals kT plus 1 over the initial concentration of the dye. And again, y equals mx plus b. In this case, we're going to graph it again, except it's going to be 1 over the dye concentration at some time versus the time, and we're going to see if it's a straight line. And whichever one gives us a straight line is the reaction order with respect to the dye. In a few minutes, we'll talk about the reaction order with respect to the bleach, but right now, Tim is going to show us how we might actually do this.
Okay, so like Colin said, I'm going to show you what you're actually going to do to determine which of those 3 equations is correct. So if we open up our Microlab software, like you guys have in the lab, I've already started a new experiment. You guys all know how to do that by now. I need to not do this, right? We need to do a spectrophotometry experiment. So we need to close that and start a spectrophotometry experiment. Now, when you open up the spectrophotometer, you are presented with some options. In the past, all we've done is click OK to move on to the next part. However, this time, because we're doing kinetics, we want to choose the kinetics option. In the lab manual, we tell you to only select one of the wavelengths. So in here, we're going to go ahead and select just the 630 wavelength. So to do that, we're going to clear all of our selections, choose just that one, and click OK. Now when we load into the Microlab, it'll be ready to do everything for us. So the first thing we need to do, as always, is read our blank. So I have got some water here that I'm going to put in the Microlab, and we're going to read our blank. It's important when you're doing this experiment that you use the larger vials that are present in the lab. They should be the only ones that are available for you in the lab. I believe I've removed all of the small ones from the lab so you don't have a choice. But there's a very simple reason. We tell you to use about 15 milliliters worth of volume, and that simply will not fit in the small vial. So once we have our experiment ready, with our blank done, we can start the experiment. This part is actually critical to how you do the experiment. So you need to mix bleach, you need to mix, you need to mix NaOH and some amount of water and some amount of dye as prescribed by the lab manual into your vial. You do not want to add the bleach yet. What will happen when we add the bleach? It's going to start to react, right? And we can't have that until we're ready. So what we want to do is I have the bleach separated into this little vial ready to add on its own, and I will add that just before I begin the experiment. So you're going to want to do this in lab as well. You're going to want to have your bleach ready to add, but not add it yet. Once I add this, the reaction starts. So what I'm going to do is I'm going to quickly add my bleach to the dye, put my cap on, shake it, put it in the Microlab, and start the experiment. The quicker you do this, the better your data will be. Because I'm kind of clumsily doing it with some stuff, it's probably going to be a little slow for me, but that's okay. We'll see what happens. So I will add my bleach, put my vial down, put the cap onto my large vial, give it a good shake so that the bleach is nice and mixed, and start my experiment. So you'll see that every 5 seconds we're reading our data. That setting is the default on the Microlab, and it's what you're told to do for the very first one. So this experiment, if you look in your microlab or in your lab manual, it tells you that you're going to run for 180 seconds. That's 3 minutes worth of time. So what should we see as time goes on? What will happen to that absorbance? It'll decrease, right? Because our bleach is bleaching our dye. Over time, there will be less and less dye present in the solution, and our absorbance will go down. So we are now currently waiting for this to go through. When it's done, I can show you a couple of tricks that you can do in Microlab to see your data in a few different ways, but we can see that the graph looks like it's flat. Why do you guys think the graph looks like it's flat, not going down at all? Because I don't have absorbance selected, right? So if I want to see how it actually looks, can I switch in the middle? I can. And then you need to select the bar you want, and now we can see that the absorbance is going down. You can see that it started around 0.6, 0.7 or so, and we're down around 0.4 already. So it's continuing on, and we need to simply wait for the reaction to go. So how will we know that the reaction has worked the way we expect it to? Good. Yeah, if you pull it out, you're going to be done, right? It's going to be clear when we take it out of that little holder. So it might not be perfectly clear, but you guys saw how blue it was originally. When we take it out, it'll certainly be less blue because we have removed, essentially, the ability of the blue dye to absorb light. So we're just going to see visually whether or not that worked. So once we're done with this, we can actually export all of this data to Excel and do what Colin was talking about, where we're going to figure out if the reaction is 0 order, 1st order, or 2nd order with respect to dye. So we can do that from this data. Once we've finished that, then we can begin working on how to determine the order of the bleach. So we're almost done here. We only have another 40 seconds left. While you're doing this in lab, it doesn't make any sense to just stand there and watch it for 3 minutes. I would recommend getting your other solutions ready so that once this one is done, you can move on to the other ones immediately. How would you respond if this does not appear to be working? What would you do? Restart it, right? If you notice that the absorbance isn't going down, if you notice that the absorbance didn't start anywhere in the first place, it's very possible that you forgot to add the bleach, that you didn't remember to add your sodium hydroxide, that you didn't add your dye, something. Well, you probably added your dye because you'd notice if it wasn't blue. But there are a few different reasons that that can happen, and you should be aware of those. So we've now got our 180-second reading done, and we can stop our experiment. So that's our data. How are we going to use that data? We're going to have to use the equation of the line of that data. So in Microlab, you can actually do some interesting things here where you can actually select through. You should be able to, at least. We'll see if it's actually working right now. It's not, so good, strong. Interestingly, the answer, as you guys probably know if you've read the lab manual, is 1st order, and it happens to be the only one that's not working right now. Oh, auto scale is not on. There we go. So, with the auto scale on, you can see that that looks pretty linear. And you can actually check on the bottom that the correlation coefficient, if you look down here, you can see that the correlation coefficient is 1 already. So we already know this is the answer, but we want to put this data in Excel because we have some other work to do. So, to do that, we need to come over here and save our data, which we can get that very loud noise in my ears. And we can export the data for this wavelength to an Excel CSV file. It's going to tell you that it's going to send you all of that data very nicely to Excel, and we simply need to save that somewhere where we can get to it. So I need to manage a touchpad, which I'm not very good with, and I'm going to name this file experiment 16 data. And I'm just going to save that to the desktop so that we can find it easily. So, save it. And now it'll automatically pull up our Excel. So, this looks pretty good. The first thing you can do when you come in here is you can delete these last 3 columns because you don't need them. So we're going to go ahead and delete those. And now you can see that we have our times listed. We can delete the second version of our time here. I'm actually going to delete it so that that row is gone altogether. But you can see that we have our time graphed versus absorbance in the B column, the ln absorbance in the C column, and 1 over absorbance in the D column. So now I want to graph all 3 of these and figure out which one is linear. Well, it's pretty easy to graph things in Excel, So I'm going to click this one and control click that one. And I'm going to insert a scatter plot of that data. And you can see pretty much right away that this is not going to be our answer. We're just going to name this time versus absorbance because that's what we've graphed on this one. And now we can go ahead and go to our second column, or our second graph rather. Again, you want to click, control click, and insert a new graph. The scatter plot is right here. Go ahead and insert that one. Well, that looks pretty darn linear to me. Oop, I'm going way over here, I guess. Sorry. This is the downside to using a trackpad, I guess. So if I scroll down a little bit, I'm going to close this for a second so that I get a little bit more space. Maybe I'm not because it's going to lag. Alright, so if I scroll down, you can see that this one is pretty linear. I'm going to rename this one as well because we want to keep track of our data. And we're going to call this time versus ln of absorbance. So now for completion's sake, just to make sure that we are correct, that is the answer, we're going to also graph our third graph by selecting column A and column D being the 1 over absorbance graph. And we're going to insert a third scatter plot, and we're going to see what that one looks like. So we can see, again, pretty quickly, that that one does not look particularly linear. So how do we check if each of these is linear in Excel? What function does Excel have to prove this to us? The line of best fit, right? So if we click on this one, if we right click and we add a trend line, we can tell Excel to give us the equation and the r squared right on the graph. Oh, I double clicked it, sorry. So we have our equation and our r squared right there on the graph. You can see that the r squared is 0.6784. That is not a good r squared, right? We want our r squared to be closer to 1 because the closer to 1 it is, the more linear our data is. So if we go ahead to our second graph, the ln of absorbance, and we right click here and add a trend line to this graph, we're going to see that that r squared is going to be pretty darn close to 1. So we're going to display our equation, display our r squared, and we see already that our r squared is 0.9995. Generally, when you have a linear relationship, you would expect an r squared to be over 0.99. In this case, it's very over 0.99, right? We're only 0.0005 off of 1. We're very close. For completion's sake, we will add the equation of the line to the third graph as well, just to make sure that that one's not linear, though of course we can see that it's not, right? We can see the curve of that line. And I'm going to just drag that over here, and we'll see that our r squared is 0.9155. Certainly closer than the first graph, but still not greater than 0.99. So therefore, we can determine from these graphs that the reaction order with respect to dye is first order, because as Colin said, that first order integrated rate law will prove to be linear if our reactant is first order. So, now that we've decided the rate order with respect to the dye, we need to determine the rate order with respect to bleach. To show you the math behind how we're going to do that, I'm going to hand it back to Colin.
All right, so now we want to look at how do we find the rate order with respect to bleach. So the dye, we did the graphs as Tim showed. He also mentioned that we also found K, the rate constant, or actually the pseudo rate constant, K prime, in this particular case. So now we want to look at how we can do it for the dye. But before we do that, I do want to show you one quick thing. If you notice, when Tim put this in, it was blue. Now that we take it out, it's clear. Did the dye disappear? No, it just got bleached. It's the same thing if you have a white t-shirt and you bleach it. The stain doesn't disappear, it just turns colorless, okay? There's still dye in there, it's just, there's that molecule, it's just a colorless version of that molecule, if you will. So, if you remember before, we had this rate law, rate, good, equals K prime, concentration dye, to the N. Well, we know that N is 1, it's first order. And we also had this pseudo rate constant equation, K prime equals K concentration of bleach to the n. But we don't know the n value. So how are we going to do that? Well, we can't use the spectrophotometer, at least not directly. Why can't we use the spectrophotometer to determine the concentration of bleach? Bleach isn't colored, it's clear. So that's not going to work. So we need another way to do it. And the way to do this is to make another solution with double the concentration of bleach. And it turns out that making double the concentration of bleach is easy. In the first solution, Tim added 1 milliliter of bleach. When he runs it in a couple minutes, and it takes half the amount of time, so it's good, when he runs it in a couple minutes, he's going to use 2 milliliters of bleach. If you use 2 milliliters of bleach, you will have double the amount of bleach. And we'll look at what happens to the pseudo rate constant based on our first order linear regression. So that gives us a new thing, K prime prime, which is equal to K2 concentration of bleach all to the n. So that has to be in parentheses like that. So we have the first pseudo rate constant where we use 1 milliliter of bleach. This is 1 milliliter. And the second one where we use 2 milliliters. Well, we have two equations. We can divide them. And it turns out that mathematically we can actually get these things. For whatever reason, we divide it this way. So we take K prime on the bottom equals K concentration of bleach to the n. This side becomes K prime prime over K prime equals, K's cancel, and what we end up with is 2 concentration of bleach to the n over concentration of bleach to the n, and the concentration of bleach comes out, and what we get is K prime prime over K prime equals 2 to the n. We can now take the log of both sides. So if we take the log of both sides, I'm going to write it over here so it'll fit on the screen. Am I still on the screen? So log of K prime over, K prime prime over K prime equals log 2 to the n. Because it's a logarithm, we can bring that outside. And what we end up with is the final equation, which is log of K prime prime over K prime equals n log 2, which now we can solve for n by dividing by log of 2. And we did all this math for you, so you don't have to do it. N equals the log of K prime prime over K prime divided by the log of 2 for this particular case. So this is the final equation that allows us to solve it. Remember that we graphed y equals mx plus b when we did the integrated rate law over here. So we have the ln of the concentration die at some time equals negative K prime T plus ln concentration die 0. And remember, this is y equals mx plus b. Said another way, the slope is K prime. So if we run this again with twice the amount of bleach and we find the slope of the line, that'll give us K prime prime. We already have K prime. We just found the slope of that original line. If we divide those things, take the log and divide by log 2, we could find the reaction order with respect to bleach. The math here is complex. What's the most important thing is to realize that we need to run it again with 2 milliliters of bleach, graph it, find the rate constant, and then just plug it into this equation.
So, as Colin said to you, we're going to need to run a second vial of bleach solution in our microlab. So, just give me a second to find my number 2 solutions. So, I don't know if you can see, but there is slightly lower volume in this container currently because we want the final volumes of everything to be the same. If the final volume of everything is the same, then that means the rate or the concentration of our dye remains the same across all the trials. If we were to change the concentration of our dye between trials, this experiment would not work. You would not be able to use this strategy because the concentration of dye would have to change every time, and we would have to take that into account for each of the solutions. So because we're keeping our final volume the same and the amount of dye that we're adding to the vial the same every time, we will be getting a constant final concentration of dye, so this experiment will work. What we are changing is the amount of bleach. This time I'm going to add twice as much bleach. So, for the second run, if you look in your lab manuals, it tells you that the time of your reading is supposed to be 3 seconds. So in this case, I'm going to change it from 5 to 3, hit OK. Now it's going to read every 3 seconds. This time it wants us to read every 3 seconds for only a minute and a half. Why is it only a minute and a half this time? Because I've added double the amount of dye, right? So the reaction is just going to go quicker. We know that there is at least a correlation, we don't know exactly what it is yet, between the rate and the concentration of the bleach. So if I increase the concentration of the bleach, as long as the bleach is not zero order, the rate of the reaction will increase. So I'm going to add it and start this really quickly, but first I'm going to take that out or else it's not going to work. So let me just add my bleach, cap my solution real quick, give it a shake, put it into the microlab, and then hit repeat. And without saving data, lose some data here and click start. There we go, we got there. Okay, so eventually we got around to it. So what's going to happen because it took me a little bit of time to get that started? What are we going to miss? Yeah, we're going to miss the initial readings, right? Does that mean the experiment will not work? No, that doesn't mean the experiment won't work. What could that mean for our data moving forward? Said another way, what's the goal of the experiment is to end when the the absorbance of the bleach, or the dye rather, gets to be around 0.1, right? Because we know that if we go too far below 0.1, our linearity falls apart. So if we run it by waiting a little too long like I did, we can simply look at the data. If the data still appears to be linear on the absorbance, or it still appears to be in the linear range of absorbance, then it's fine and we don't have to do anything. If we go too low, below the linear range of absorbance, we can simply unselect the peaks that are below that range. So we will see what our data looks like when we get to the end here. It's currently more than 2/3 of the way through. You'll see that these are each more quick than the last, and you'll see again the graph is appearing pretty linear because I have the ln of absorbance selected. The ln of absorbance in this case does not tell us anything about the reaction order of the bleach because the absorbance is only related to the concentration of the dye. So we need to let this finish and then do the math that Colin showed us to be done with our answer. So if I click stop, we will finish our reaction. So if we just go over to the absorbance real quick and just see where we ended up, we can see that we ended up kind of low. So we might have to unselect some of our data points. But that'll be obvious when we go to our graph. If we go to our graph and our line stops appearing linear, then we know that we need to stop those things. So I'm going to go ahead and save that data. Once again, I'm going to export that data to a CSV file. It's going to tell me that it's going to give me everything again. I'm going to say, okay, this is going to be experiment part 16, part 2, and I'm going to hit save. So now it's going to bring up all this data. Do we want this data on a different sheet than our original data? No, right? We want it on the same file as our other. So to do that, all we have to do is select all of our data. I'm just going to move everything, go back to our original file, and paste that data in. So if I can scroll this back up to the top, I'm going to go ahead and delete my other 2 graphs just to save myself the space, or rather just that one graph to save myself some space. And I'm going to delete this graph as well so that I can just keep this important graph in view. And I'm going to paste nothing. I will paste nothing. So I'm going to reselect that data. Excel gets kind of picky about when you can and can't select, or you can and can't copy and paste data. So it may have just gotten picky there. So let me just select back into here, re-click here, and paste. Alright, So now we have all of our data. So what do we need from this data? What did Colin say that we need from this data in order to find our reaction order with respect to the bleach? The slope, right? The slope of which line? Do we want time versus absorbance, ln, or 1 over absorbance? ln of absorbance, right? Because that's our linear one. So if I go ahead and again, I'm going to delete some of these columns here because we don't need them, and it will save us some space, which is obviously at a premium. I'm also going to go ahead and delete the columns that we know we don't need other than the ln, right? Because we've already determined that we want to use the ln column. So I'm going to delete all these to save myself some space. So now if I select these two columns, I will go ahead and insert another scatter plot. And this one will be, if I can get rid of this for a second, sorry. If I can select this, we want to keep all of our stuff labeled at all times. If you don't keep your material labeled, it's very easy to lose track of things. So this will be time versus ln absorbance, spelled correctly and everything. Absorbance, trial 2. So that's just for our sake so that we can keep track of it. So if I click on here and I add my trend line, I need my slope, right? So I need my equation. We're going to display our r squared just to make sure it's close to 1. And then I'm going to close out of that window, and we will see that our r squared is a little low. Our r squared is 0.9878. Can anyone see from the graph why our r squared might be a little low? Because when we get to the end, that line gets a little curvy, right? It's not necessarily a straight. So I said when we were graphing this that it was possible that our data would end up being a little off because we started the experiment late. So I'm going to just unselect some of those data points. So I'm just going to cut off the bottom 10 or so data points on both the X and Y. If you select the data on the graph, it'll show you these colored little bars and let you select. And you can see in the corner here that our R² has gone up to 0.99. So this is good. That means our data is usable. So now we have both our slope of our first graph and our slope of our second graph, so we can use that to calculate our n. So I'm going to go down here and I'm going to do the calculation of n. So to do that, we need to take the log of k prime prime over k prime and divide that by the log of 2. So in Excel, to do that, we need to type log 10. If you don't type 10, it's going to do the natural log, which will not work out well for you. You will be using base E, Euler's number, instead of base 10, and you will be unhappy when you do that. So we're going to do k prime prime first. What is the value of k prime prime on our graphs? It's the negative slope of our second graph. So it might be a little hard to see, I'm not sure, but with a touchpad it's hard for me to change the font size. But in this case, that slope is 0.0329. And then we're going to divide it by k prime. K prime is the slope from our first graph. In this case, it is 0.0148. Then we're going to divide all of that by the log of 2, right? So we do again log 10 of 2, and we hit enter. And we see that our order with respect to bleach is 1.15. Can the order of a reaction be anything other than a whole number? No, right? So is 1.15 our answer? No. What should we do with that 1.15? Round it down to 1, right? It's very close to 1. It's only 0.15 off. So if we just use 1 as our number, we find that our reaction order is 1 with respect to bleach. So now that we've found our reaction order with respect to bleach, you'll remember that Colin showed you an equation of the rate of k prime being equal to k times the concentration of bleach to the n. So now we have a value for k prime. We can calculate the concentration of bleach, and we know that n is 1. So for k prime, we can figure out what our rate is, or what our rate constant is. So now we're going to calculate of k. So to calculate that, we're going to do, from our math earlier, it's going to be k prime divided by the concentration of bleach. The concentration of bleach calculation will take you a little bit of work. But when we do that, we'll find that the concentration of bleach is 0.047 molar. So we're going to take our K prime, which is 0.0148. We're going to divide that by the concentration of our bleach, which is 0.047. So we'll find that K is 0.314. So when we do things in lab, do we ever do them only one time? No, we do them repeatedly, right? So how can we do this measurement repeatedly? We can use the different concentrations, exactly. So we've repeated this experiment multiple times. So this was for the first trial. So now we're going to do it for the second trial, which the only difference between the first trial and the second trial, we have a different concentration of bleach, right? We doubled our concentration of bleach, and we also have a different K prime, in this case K prime prime. So we're going to take our K prime prime, which is 0.0329, divide that by double the concentration of bleach, which is 0.094, and see that we have 0.35. Those numbers are pretty close. In lab, you will not do 2 trials, you will do 4 trials. Once you've done all 4, you can take the average of your Ks. Like I said, I only have 2, you'll have 4, and you'll find that the average K for our values is 0.332. And that is the number that we can report in our final lab report. Some important things to remember when you're performing this lab. Up here, when we calculated n, we did log of K prime prime over K prime divided by the log of 2. If I were to triple the concentration of bleach, which I will in the third trial, can I use this same equation? No, right? What's going to change about this equation? I'm not going to divide by the log of 2, right? That 2 came from us doubling the concentration of bleach. If instead I triple the concentration of bleach, guess what number I'm going to have to take the log of instead? 3, exactly. So for the third trial, we'll have to take the log of 3, and then for the fourth trial, we will have to take the log of 4. So please remember that you're doing that when you do the various trials. The only other thing that will change is each time you need to remember that up here, the 0.047 is our calculated concentration of bleach. That number will change each time as you add more and more equivalents of bleach. If you don't change that number, of course, your experiment will not work correctly and you'll have bad data. Okay, so to find the concentration of bleach, if you look in your lab manual, I forget what page it's on exactly, but it tells you what the concentration of bleach is in the initial solution on the bottom of one of the pages. I just don't know where it is off the top of my head. But in any case, it is in the lab manual somewhere. I just can't find it right now. But it is in the lab manual, the concentration of the bleach, and then you can use the dilution equation because you know how many milliliters of bleach you're using to calculate the final concentration of the bleach. Another strategy is we tell you the first 2 values, and from there you can figure out the third and fourth value by extrapolation. Are we done recording? Okay, so just give me a second to stop recording, and we will answer questions.